Hello friends, welcome to another lecture on control system series. In this lecture we will be discussing on Routh Hurwitz criteria, also known as RH criteria. I plan to divide RH criteria video into 3 to 4 videos where the first part will discuss on RH criteria conditions and the method of applying RH criteria. Second part will focus on two special cases, that is a 0 in the first column and a 0 row. Moreover, the second part will focus on how to calculate gain of a system as well as frequency of oscillation if the output response is oscillating. In part 3 and 4 we will see selected IES and GATE questions which will cover all type of questions you can expect in an exam. Now starting our lecture, the major concern in designing a system is where do poles of the system lies, because the poles determine stability of a system. So we have seen in our previous lecture that a left hand side pole gives a decreasing response where the output response of a system continuously decreases, while a pole in the right hand side gives a response in which the output amplitude continuously increases. This kind of response makes the whole system unstable. So even there is one right hand side pole in the whole system, it will make the whole system unstable. And the third condition is the poles being on an imaginary axis, for which we get an output response that is oscillating. To find the location of poles is easy when the transfer function is given in a factored form, as you can see here. Now for this system, we can see that the poles s plus 2 and s plus 3 will give a response that will be decreasing. So these are stable poles and they will give a stable response. But s minus 4, which is a pole lying in the right hand side of the imaginary axis, will give an unstable response, that is the output will continuously increase, because of which the whole system becomes unstable. But let's take a practical scenario where the transfer function is not given in the form of factors, but it is given in the form of a polynomial equation. These equations are of very high powers and it is very difficult to factorize them, especially without a computer. Now the RH criteria solves this problem where it can predict the stability of a system based on certain operations on the coefficients of these polynomials. Thus, we do not need to factorize those complex high-power equations, and yet we can find whether the system is stable or not. So without wasting any time, let's see what are the steps involved in RH criteria. The first step. In the first step, we will identify what is the characteristic equation of a system. Now every system is represented by a transfer function, and a transfer function has a numerator and denominator. Poles of any system are based on denominator, and it is the poles which determine the characteristics of a system. Therefore, a denominator is taken as a characteristic equation for finding out whether the system is stable or not. Now suppose a transfer function gs is given, which you can see. Now suppose that the system is an open loop system, then the denominator of gs becomes the characteristic equation. Now consider a closed loop system with unity feedback which uses the system gs in the forward loop. On using the equation of closed loop system, you can see that the denominator is 1 plus gs. Therefore, we will take 1 plus gs as the characteristic equation to find the stability of the system. After we have identified the characteristic equation, we will move on to step 2. In the step 2, we will look for any sign change in characteristic equation. As you can see from this example, the coefficient of S2 and S0 are positive, while coefficient of S is negative. So here you can directly conclude that the system is unstable, because at least one right hand side pole is needed to introduce a negative sign in the characteristic equation. Moreover, when we plot this characteristic equation, you can see there are poles at two positions and both are on the right side of the axis. Hence the system is unstable. However, there is an important thing to note. All negative coefficient does not mean system is unstable. So let's see an example. Now in this example you can see that all coefficients are negative, but you can remove the negative sign to convert it into a positive equation. So here we cannot confidently say whether the system is stable or not. Another important thing to note is all positive coefficients does not imply that the system is stable. Let's take an example. Now you can see that this is a polynomial with all positive coefficients. But when we factorize this polynomial, you can see that one of the roots has negative components. This implies that the overall system is unstable. Even when we plot this equation, we can see that there are roots on the right hand side of the axis, which directly implies that the system is unstable. Step 3. In this step, we will see if there is any missing power of S. Let's take an example where power of S square is missing. This directly implies that the system is unstable because at least one S minus A term is needed to cancel any power. From the plot of this equation, we can see that it has roots on the right hand side of the axis, as well as from the impulse response we can see that the system is unstable. Therefore, if you see any power of S missing in the system, you can directly conclude that the system is unstable. However, there lies an exemption where when the characteristic equation has only odd or even powers of S, then you cannot be sure that whether the system is stable or not. You can see a couple of examples here. In the first example, all the powers are odd. In the second example, all the powers are even. However, in this case, you can conclude one thing, that there will be no real roots, but only imaginary roots. That is, the output response will have sustained oscillation only. In the plot of this function, you can see that there are only imaginary poles and no real poles, and thus you can conclude that the output will also be oscillating. Let's consider two equations, both having only even powers of S. For both of these equations, you can see the location of their poles in the plot. Both of these equations have only even powers, both will give you an oscillating output, and both have only imaginary poles. But the first one, there are poles on the right hand side of the imaginary axis, while for the second, there are poles only on imaginary axis. For the first, you will get an unstable response, while the second is a marginally stable system and it gives an oscillating response in the output. Now, when none of the above conditions are met, then we need to perform the RH operations. So let's take an exemplary equation and learn what are these operations. The first step is to draw a vertical line. On the left hand side of the vertical line, place the power of S in the decreasing order. Now here we can see that our equation is of the order S raised to power 6. So S raised to power 6 will be the first entry on the left hand side of the vertical line. After that, we will write the powers of S in the decreasing order from S raised to power 6 to S raised to power 0. Having done that, now we will fill the first two rows on the right hand side of the vertical line. The first column will be filled with respective coefficients of S raised to power 6 and S raised to power 5. So here we will directly put the coefficient of S raised to power 6 and S raised to power 5 from the given equation. Once we have done that, for rest of the columns, we will alternatively take the coefficients and put them. In other words, we will reduce the power of S by 2 and then put their coefficients in each column. So for example, in the second column of the first row, you can see that we have put the coefficient of S raised to power 4, which is 2 less than S raised to power 6. Similarly, in the second row and second column, we have put S raised to power 3, which is 2 less than S raised to power 5. Again, moving on to the next column, that is the third column. For the first row, we will be again decreasing the power by 2. So we will put the coefficient of S raised to power 2 in third column and first row. Similarly, for third column, second row, we will decrease the power of 2, that is S raised to power 1's coefficient will be put in this place. In the fourth column, we will again decrease the power by 2, that is power of S raised to power 0 coefficient will be put here. And since there is no power to be decreased further, we can leave the space empty or we can consider it to be a 0. Once we have filled the first two columns, now we will calculate the values for third row using the values of first two rows. Now suppose that the third row values are B1, B2, B3. So the value of B1 will be given by this equation, where you can see that A5, A4 minus A6, A3 upon A5. Now we see that the procedure follows the path as shown in the matrix, where A5 into A4, then we subtract it with A6 multiplied with A3, and then it is divided with A5. So we will follow the similar path for each calculations. Similarly, we will calculate for B2. We will follow the same path using the first column and the third column now. Following the path, we will get A5 into A2, which is subtracted from A6 into A1 and then divided by A5. Similarly for B3 we will follow the same path. However, here one of the values is 0. So what we will get is A5 into A0 minus A6 into 0 upon A5. Now we will calculate the values of fourth row in similar fashion. Now suppose the values of fourth row are C1, C2, C3. Now the values of C1 and C2 and C3 will be calculated using the two rows just above S cube, that is the rows with S raised to power 4 and S raised to power 5. We will follow the similar operations that we did for B1 and we will get the results as you can see. We will do the same procedure for all the rows. To understand the operation more clearly, let's take an example and perform these operations. Now here you can see the transfer function and we will take the denominator of this transfer function as a characteristic equation. Here we can see that none of the previous criteria which we mentioned from step 1 to step 3 are satisfied. So we will draw a vertical line, and as you can see the highest power in this characteristic equation is S raised to power 5. So the first entry will be S raised to power 5 on the left side of the vertical line, and then we will write all the powers of S in the decreasing order till S raised to power 0. Having done that, on the right hand side we will populate the first two rows, that is the rows of S raised to power 5 and S raised to power 4. To start, we will write the coefficient of S raised to power 4 in front of it and the coefficient of S raised to power 4 in front of it. Having done that, for other values we will decrease the power of S by 2 for each column and then populate their coefficients respectively. Now here you can see that we have populated the first two rows. Now let's calculate the values for third row, that is the row of S raised to power 3, and this row's values will be calculated based on two rows just above it, that is S raised to power 4 and S raised to power 5. So here you can see that we are calculating the values of third row using the formula we discussed earlier. Now similarly we will calculate the values of S raised to power 2 row. We will use the values of S raised to power 4 and S raised to power 3 for calculating the values of S raised to power 2. Now for the calculation we will follow the similar path where we will take the value of the first column and then we will multiply it by 4, then minus 1.55 into minus 1.66, and we will get the result by dividing it with minus 0.66. Please do the calculations to match your answer. Similarly, we will complete the values in all rows. Now we will analyze the first column. Here we can see that when we go from S raised to power 4 to S raised to power 3, we see that there is a sign change. That is a sign change from positive to negative. And now when we go from S raised to power 3 to S raised to power 2, there is again a sign change from negative to positive. So here we can see that there are two sign changes, which by RH criteria implies that there are two poles in the right hand side of imaginary axis, thus making the system unstable. From the plot of the characteristic equation, you can see that there are actually two poles on the right hand side of imaginary axis. And from the impulse response, you can see that the system is unstable. So here we can see that simply by analyzing the sign changes in the first column of this matrix, we can conclude whether the system is stable or unstable. Now there is one thing to note. If a power of a S is missing, we will take the coefficient to be 0. Let's take this example. Here you can see that the power of S raised to 1 is missing. So when we are populating the values in the first two rows, we will take the value of S raised to power 1 as 0. Let's do a recap of all the steps involved in RH criteria. The first step is identifying the characteristic equation. Now when it's the open loop system, the denominator of the transfer function becomes the characteristic equation. But when there is a closed loop system, we will use the closed loop formula of Gs upon 1 plus G. 1 plus Gs is taken as the characteristic equation. In second step, we identify that whether there is any sign change in the characteristic equation or not. If there is a sign change, the system is unstable. In the third step, we look if whether there is any power missing in the characteristic equation. If there is any power missing, the system is again unstable. However, there does lie an exception where all the powers are odd or even. In the final step, where all above criteria are not met, then we will apply this RH criteria and we will see whether there is any sign change in the first column of the. If there is a sign change, then there are poles in the right hand side of the imaginary axis. The number of poles in the right hand imaginary axis is equal to number of sign changes in the first column of the RH matrix. Now let's see the uses of RH criteria. RH criteria helps you to find the maximum value of a controller gain, whether it is a closed loop system or an open loop system. For example, here you can see a closed loop system where there is a controller gain whose value is k. So by using RH criteria, you can identify the maximum value of k for which the system does not become unstable. Now for oscillating systems, RH criteria helps us to find the frequency of oscillation of the output. RH criteria also helps to find relative stability of a system with respect to a given axis or a given point. We will discuss all these three use cases along with two special cases of RH criteria in the following lectures. Please stay tuned. If you like the video, please subscribe the channel and share it with your friends. Thank you.